Start off with an ideal gas equation. Okay, PV is equal to nRT. This is the macroscopic view. Okay, first view. Measurable quantities. P, V, T, even N. Then they come to the second view. It's a theoretical view because you can't see the molecules, you can't get the velocities. But here in this, they are relating the pressure to the number of particles and the speeds. What they do is once they relate the pressure and the volume, PV, they have related PV to the RMS and the number of particles. Then they have related PV to kinetic energy, half mv square. That's why the term kinetic theory of gases. Once they do that, they can, because they know PV is equal to nRT, then they relate nRT to the kinetic energy of the particles, total particles. And once they know that, they can get to kinetic energy of one particle. And that is this. So they have found using the pressure, easily measurable volume, temperature, we ended up with allows of a particle by measuring only its temperature. So from PVT, the macroscopic, we can find the kinetic energy of a particle, and we find it is only dependent on T, nothing to do with P and V. Now, if you know this, then there's something which comes up, Boltzmann constant K. So essentially, this to equation is very easy. You can remember this. You will find R here as the, and that can be done as KB into N, the Boltzmann constant, and N is the number of particles. And this is not Avogadro number, it is the number of particles. Now, uh, if you notice here, here he says N is the number of particles and N is the number of moles. Now, number of moles into Avogadro number is N. So be clear that whenever N comes, it is just the number of particles. This is moles, this is number of particles, and this is Avogadro constant of 6.02 into 10 to the power 23. And this N by N is nothing but the, uh, I mean, 1 by NA, whatever. Ratio, just you can actually remember. I don't know why they've written N is equal to N by NA, number of particles by Avogadro constant. That's the number of moles. So what have we got? We have got these equations. One, PV is equal to this. This is KB into nRT. And what is this? This is the total. I mean, one is you have got the connection between PV is equal to nRT. You have got the connection PV, P is equal to velocity, P dependence on velocity. Then you have got a connection of kinetic energy dependent on temperature, kinetic energy dependent on temperature. And once you know that, then you can get the velocity by dependent on temperature. So velocities is kind of dependent on the pressure. Pressure and velocity are connected, and velocity and temperature are connected. And you can get, this is the energy of one this thing, and you can, if you of the whole, sorry, the total, because kb into n, if they say kbt, That's one particle. Okay. If the kb n into t, it's 3 by 2 RT. That's the whole gas. So you be clear about this. So we know the energy of the total energy. Here we this is total energy, this is single energy. That's why he says, na, he says here, look, kb kt. This is 3 by 2 kt, na. Here what is he saying? Here he is saying 3 by 2 kb into nt. So this is for uh, the whole sample, all the gases, all the particles. Okay. So now whenever we do question, so we got these 3, 4 relations. I can get the kinetic energy with respect to time of one particle, of all the particles, pressure and volume connected to energy, and pressure and volume to this. These are the 3, 4 relationships. So we'll see what the question is asked. Make a note, right? One is that pressure is dependent on rho into C RMS square, one relationship. Then P is equal to, if they give you the number of moles and number of molecules and the mass, then you can use this relationship. Otherwise, you can use PV. This is the other relationship. Then PV is equal to uh, this one, 2 by 3, 3 by 2, 2 by 3 E. So this relationship. Why this comes about is because this we so we can come this, if you see this, if you are given the mass and the of one particle, and you know the kb and the temperature, you can find. But this question was not asking you. Okay, this question is uh he's saying that we use this p is equal to 1 by 3 rho square. So p is given, and this is given, and so we can calculate. You just visualize that there is a big box. You say the pressure it is exerting on all this P, the volume of this is V, and the temperature is T. Then you take a particle, you do two, 3 particles, and then you say the kinetic energy of each particle is this 3 by 2 kBT. You write the kinetic energy. Where was I doing it? Yeah, the kinetic energy of this each particle, half mv square. Okay, half c1 square, right, is equal to uh 3 by 2 kbt. 3 by 2 3 by 2 kbt. Then you say the total energy is 3 by 2 kb into nt. Then you say this is total energy, k of one particle, and you write total here. Okay, E total. Then you say that this E total is connected to PV 2 by 3 at this here. PV 3 by 2. That means PV 3 by 2. Now, why did this 3 come? Because this 3 has come here. So 3 will go here. So remember, this 3 by 2 PV is equal to energy. So effectively, what you're going to do is you're going to remember this like 3 by 2 PV is equal to the all these energies together are connected to this. That's how the temperature PV is connected to nRT. This nR and this are all connected. Okay, that's how this 3 by 2. Like if I write this PV is equal to 2 by 3 E, then E is 2 by 3 into 3 by 2 kb nt. So this will become kb into n is RT. And no, kb is Kb is R by N. R by N. Avogadro. This is he's showing here. See. Here he's saying Kb by RNA. So when I did this na PV is equal to 3 by 2, sorry, 2 by 3, 2 by 3 E. E is nothing but 2 by 3 into 3 by 2 Kb into NT. Now 3, this will cancel. Kb into N. Kb is R by Na. So N by Na is nothing but N RT. So that's how PV is equal to nRT. You derive a few of it, so that you can get a feel of them. You have related the kinetic, the speed of the molecule to the macroscopic properties.